Hi, everybody. This is lesson 1 for our organic chemistry introduction. Just wanted to remind you that this is going to be just a very brief introduction to all of the things that organic chemistry is going to cover. So we're just really going to scratch the surface of what organic chemistry is during our last few weeks together. You have to go along with this video. You have this paper or this Google Doc. It's called Organic Chemistry Lesson 1. You can find it on Brightspace. It might be a good idea if you watch the video on one screen and you fill out the note sheet on another. This just might make your life a little bit easier. That way you don't have to flip back and forth between screens if you're not printing this out, which I don't expect anybody to be printing out. So maybe put me on your phone and have your Chromebook or your iPad with the note sheet up. That way you can do both at the same time and pause me when you need to. So with that, we are going to start looking at what is organic chemistry. And the first thing that we have to talk about or refresh your memory is just what is carbon and how do we draw it. So it says to draw the Lewis structure or the Lewis dot diagram for carbon, which if you go back in your memory bank, you know that carbon looks like this. It's got 4 valence electrons, 1 on each side. So it gives you a space to bond to each side of the carbon atom, which makes carbon kind of special. And the reason that it gets its own kind of branch of chemistry, it all has to do with that carbon has those 4 spots to bond with. So organic chemistry, this is going to be compounds that contain carbon atoms. They're usually bonded with other carbon atoms and hydrogen atoms, and sometimes, which is why we call them hydrocarbons. So organic chemists are going to deal a lot with hydrocarbons. It's just a combination of hydrogens and carbons bonded together. Other atoms can be present within organic compounds, but it's a small list of things that are going to be included and still be organic. So anything that's a halogen, so in that the row on your periodic table right before you get to the noble gases, like chlorine, fluorine, those guys can be part of organic compounds. And then other nonmetals like nitrogen, oxygen, phosphorus, and sulfur. So organic compounds are a combination of those specific atoms bonded to each other. Some examples, you don't have to draw these, but I just thought I'd give you a few examples of some organic compounds. So the first one is isooctane. So this is a kind of fuel. Notice how these pictures get kind of crazy. These structures get big pretty fast. But we are just going to be starting looking at them. Another example is DDT. This was a pesticide that was used a while back. We actually realized that it was very harmful to bird eggs. So if you have heard anything about the history of our bald eagle populations and them going very far down, it's because we were using DDT to kill plants or kill pests so plants could survive. But then we realized that it actually kind of eats away at the shell of these eggs, and then baby birds don't survive either. So we don't use DDT anymore, and the bald eagle population has been able to come back up. Just an interesting biology side note. That you might be familiar with would be testosterone, which is a hormone that we have present in our bodies. We also have the organic compound nicotine. So all those people that spent a lot of time this year vaping in the bathroom, it's because they're addicted to that organic compound nicotine. Don't smoke, don't vape. It's your PSA for today. Cocaine, a little bit more severe than nicotine. Also don't do cocaine. Another PSA for the day. But cocaine is found, it comes from a plant, so it's an organic compound. And then finally, an example that you might be familiar with is Teflon. Teflon is often used as like a coating on cookware, and it makes it non-stick. But the bad thing about Teflon is you cook and you scrape those little Teflon bits into your food. There's been some studies about how Teflon may not be the best for us to eat. So even though it's organic, doesn't mean it's like safe to consume. Yeah, Teflon. So, when we are looking at organic compounds, that word organic in your frame of mind might mean like healthy or from nature, like organic produce in the grocery store. That's not necessarily true. And scientists used to think in order to be organic, it had to be like alive or have some kind of like life force. But that was proven wrong actually back in 1828, so a very long time ago. They took an inorganic salt, so this ammonium cyanide. They took that and they took it through a process where they heated it up and they actually produced an organic compound, urea, which is found in our urine. So they could see that in order to be organic, it didn't necessarily have to come from a living thing. It just had to get to the point where it was only including those compounds that are classified as organic. Inorganic carbon compounds can be a little bit confusing and cause a little bit of problems because just because it contains carbon doesn't mean it's organic. Most of the time, carbon-containing compounds are organic, but if you have carbon bonded with other nonmetals, so those ones that were on our list, if you had any other nonmetals bonded with carbon, that would be classified as inorganic. And then carbon bonded with metals would also be inorganic. So simple hydrocarbons, we're going to take a second. I'm going to pause and go up to the whiteboard and draw you one of these in a second. But we just want to recall that we're going to start carbon with 4 valence electrons each time so that carbon can make 4 covalent bonds, one on each side of its carbon atom. There's going to be millions of these organic compounds, and we are going to start with the simple ones. So I'm going to pause, go up to the board, and show you how to draw one of these. All right, the sample problem that we're going to go through together comes from your note sheet, and it says we are going to draw the structural formula for butane, which is that fuel that you use in like a lighter to light your campfires or your candles or whatever you're using lighters for. And the formula for butane is C4H10. So C4H10. It's a hydrocarbon because it's carbon and hydrogen. Hydrocarbon. And we are going to draw just the structural formula. So there's spaces on your note sheet that talk about condensed structural formula and carbon structural formula. We are not going to worry about those because, like I said, we're just doing a very brief introduction. We're not going to go any deeper than structural formula for these. So when we start doing our hydrocarbon, we are going to start by putting all of our carbons in a straight line and bonding them together. So I have 4 carbons, carbon, 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 and I'm going to bond them all together. So carbons have those 4 valence electrons, meaning they can bond in each position. So after we get our carbons all together, we're going to add our hydrogens on to fill everybody up. So this first carbon here, this spot is already taken, but I could bond a hydrogen here, here, and here. So I'm going to plug 3 of my hydrogens into that one. My second carbon is full on 2 sides, so I'm only going to put hydrogens in the empty spots. Same thing for the next carbon. And then finally, the last carbon is just like the first one, where I can put 3 carbons on, or 3 hydrogens, I'm sorry. So when we get to that point, we have our 4 carbons bonded together, 1, 2, 3, 4, and then all of our carbon spots are filled up by our hydrogens. So we have, if I want to count, make sure I have 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This would be the structural formula for butane, where I have C4H10. Last thing we're going to talk about today is our first group of simple hydrocarbons, which is the alkanes. So these are going to be hydrocarbons that only have single bonds. So the one I just drew, notice I only used single bonds to get that all the way filled up with hydrogen. So that would be an alkane. The other thing about alkanes is that they are saturated, which means that there is no room for other atoms to bond to the carbon skeleton. The whole thing is saturated with hydrogens. There's no empty spots. When you have an alkane, you have a simple formula to follow, which is this CnH2n plus 2. So that is the chemical formula for an alkane. It just means however many carbons you have, you're going to have this many hydrogens. So if your N number was 3, you had 3 carbons, you would end up with 2 times 3 is 6 plus 2 is 8. So if you had 3 carbons, you'd end up with 8 hydrogens. We just drew 4 carbons, 10 hydrogens. The alkanes follow that pattern. And then we have a set of prefixes that help us name alkanes. And you have a chart to fill in 1 through 10. These prefixes are a little bit different than any prefixes we've had in the past. I'll just go through. We have, I'll put that up there too. So if you have 1 carbon, you would name it methane. 2 carbons would be ethane. 3 carbons would be propane. 4 carbons would be butane, like the example that we drew. And then the rest of them are going to go through penta, hexa, hept, oct, non, and finally decane if you have 10 carbons. So we're going to stop there. It might be a good idea for you to pause the video on this spot so that you can fill out that chart, because you are going to be needing that chart for our next lesson, where we're going to be drawing some of these hydrocarbons. So fill out your note sheet. I will have the note sheet answers posted on Brightspace so that you can kind of go through and check. But that is the end of lesson 1 for organic chemistry.